Let's have a look at this handout about non-right triangles. So as I said in the introduction, before you watch this video, you should spend some time working on the problems in this handout and only watch the video if you get stuck or if you solve a problem but feel like you could use some extra explanation. So with that said, I'll pause the video now and work on this first problem if you haven't already. Okay, so let's see what we can make of this. So we want to find this length A in the upper right, and this isn't a right triangle. You can tell it's not a right triangle because the two angles at the bottom that we know, let's see, 75 degrees plus 50 degrees, that's 125 degrees, which means that the angle at the top must be, let's see, 55 degrees, I guess. So it's definitely not a right triangle, but we only know about right triangles, right? Trigonometry in triangles, trigonometry is all about right triangles. So if we could make some right triangles appear, we could maybe make some progress. And there seem to be a few different ways to make a right triangle appear. Kind of what my eye wants to do is drop a perpendicular line down here. So this line is perpendicular to the bottom, and it makes two right triangles, one on the left and one on the right. It's sort of tempting to think that this line that we've added to the picture bisects the angle at the top, but it doesn't actually. We don't know for sure if it does. In fact, it doesn't. So you can't assume that, right? We can draw a line that makes this bottom angle a right angle, or we could draw a dotted line that bisects the angle at the top, but there's no guarantee we can draw a line that does both at the same time. Since we're looking for right triangles, I decided rather than bisect the top, let's make this bottom angle a right angle. Okay, now that we have a right angle down here, we know an angle and we know a side. So we could use trigonometric ratios to find any other side in this right triangle. Since our goal is to find A over here, way over on the right-hand side, it seems like if we could use B to find this middle, the height of this, the length of this middle line, let's just call that H, I guess, and then we'll know H and this angle capital B, and then we could use another trigonometric ratio to find little a. So that sounds like a plan. So we're going to use B, little b, and capital A to find H, and then use H and capital B to find little a. So if that plan seems achievable to you, then pause the video now and execute that plan and see what you get for A. Okay, let's go ahead and work out finding A. So on the left-hand right triangle, we have, let's see, we have the hypotenuse and H is our opposite side. So we should use a trig function that has an opposite side and a hypotenuse, and that's going to be sines. So sine of the angle A, which is 75 degrees, is the opposite side, which is H, divided by the hypotenuse, which is B, that's 2. Now this trig function on the left, sine of 75 degrees, we can use a calculator to approximate that. Make sure you're in degree mode here. 75 degrees isn't one of the nice angles, so a decimal approximation with a calculator is really the best we can do. It looks like sine of 75 degrees is 0.9659. So that's H over 2. And then we can solve this for H. So H is 2 times that messy decimal. That's 1.932 approximately. Okay, now that we have H, we can go ahead and find A. On the right triangle on the right, again, we have the side opposite the known angle. 50 degrees is our known angle. So we have the side opposite that, and we have the hypotenuse, which is A. This time A is what we're looking for instead of what we know, but still it's one of the sides involved. So sine of 50 degrees is H, which is 1.932 divided by A. And then we can solve this equation for A. Rearranging things, we get H equals 1.932 over sine of 50 degrees. And we can dump that into a calculator. Again, 50 degrees isn't a nice angle, and so the best we can do is a decimal approximation. All right, so our previous result divided by sine of 50 degrees gives us 2.522. All right. And I guess that looks about right. If this side B is 2, then maybe A could be about 2.5, and the height of this thing might be 1.9. That seems plausible. I think the picture, when I made this diagram, it's not quite to scale. It's not too far off, but it's not exactly right. Okay, so if all that made sense, then pause the video, scroll down to number 2, and see how it goes. All right, so here's number 2. So the angle C, I gave this away. That's 55 degrees, I think is what we found up above. Yes, 55 degrees. Okay, so now we need to find the length of C. Well, so A we know, A was 2.521, and we know the angle C. And, well, I think there are a couple things we could do here. Drawing a perpendicular line down to the bottom side let us sort of jump the gap from B to A. So maybe drawing another perpendicular would let us jump the gap from B to C. So let's see, I guess that would be maybe like this. I guess before we do that, it's tempting to just use the Pythagorean theorem because this is a triangle and the sides are called A, B, and C. But remember, the Pythagorean theorem only applies to right triangles, and our main big triangle here is not a right triangle. Okay, so if we draw this extra diagonal line here, we can draw it so that this angle is a right angle. So now we have some right triangles to work with, and then we can kind of play the same game that we did in the last one. So first, let's call this diagonal here. Let me reuse the value h, I guess, or the name h. So sine of, this time 55 degrees is the angle, and that is going to be h over 2. And so h is 2 times sine 50 degrees. Sorry, 55 degrees. Okay, now we can dump this into a calculator. 2 times sine 55. We get 1.638. Okay, so that's the diagonal. And now we need to find C, but again, we have this lower right triangle. The known angle in that one is 50 degrees, so sine 50 degrees is the adjacent side, the opposite side, which is h, which is 1.638, over the hypotenuse, which is c. So c is 1.638 over sine of 50. Okay, so 1.638 divided by sine 50. Okay, that's 2.139, I guess. Okay, so that seemed to make sense. If that made sense to you, then pause the video here and scroll down to number 3 and see if you can make progress on it. Okay, here's number 3. So you may have gotten the sense in those last two problems that we were kind of doing the same thing, but just with different numbers. And whenever you get that feeling, that is your brain sort of telling you that there's a general formula or a general process that we could figure out. So let's do that general process. Here's the general setup. We have an angle A in a triangle. We have an angle B. And then we know the sides, we're going to suppose that we know the sides opposite those angles. So notice that I have my names set up so that the angle capital A is opposite the side little a, and the angle capital B is opposite the side little b. So if you know a pair of opposite angles and sides like this, then what we did before was we drew this line down the middle to make two right triangles. And then we sort of follow this chain of trig functions to this middle height and then over to A. So let's see how that works out. So let's see, in the triangle on the left, we have sine of A is h over b. And then in the triangle on the right, we have sine of capital B is h over little a. But for both of these, we can, right, the only variable that these two equations have in common is h. So let's solve both of these for h. So this first one gives us h equals b times sine of capital A. And the second one gives us h equals a times sine of capital B. All right, but look, both of these are h. So now we can eliminate h just by setting these two things equal to each other. So I guess I've done a and b already. So go down to c. We get little a times sine of capital B equals little b times sine of capital A. All right. Some people don't like having the letters mixed like this, and so they divide both sides by AB, and some stuff cancels, and you get sine of B over little b equals sine of A over little a. Okay, nice. This sort of has a pleasing symmetry to it. So if that made sense, then pause the video, scroll down to the next problem, and see how it goes. Okay, so hopefully you've read this already, but this equation that we got on the previous page, just by relabeling sides, it's actually sine c over little c is also equal to the same thing as the other pair of side angle pairs. So it's sort of an interesting fact about triangles that these ratios are the same for a single triangle. If you drew a different triangle, these three ratios would be different for your different triangle, but all equal to each other for that triangle. So each triangle has its own sort of characteristic value for the sine of an angle divided by the length of an opposite side. And this fact is called the law of sines. So that's its name right here. And you can use the law of sines to find unknown things in a triangle. So here's a triangle. Let's give it a shot. We're going to try to find the angle B right here. And we know some other sides and angles. So let's see, we know capital A and little a. So when we write down the law of sines, we should definitely use the version that has a in it. And we know little b, and we want to know capital B. So we should also use the version of the law of sines that has b's. So these are both equal to sine c over little c, but we don't need to use that right now. Right? C just isn't something we're interested in at the moment. Okay, so now we can put in everything we know. Sine of 85 degrees over little a is 5 equals sine of b over, we don't know b, so we have to just leave it as capital B, over little b, which is 1.5. All right. And we're looking for capital B, so we can just solve this equation. multiply both sides by 1.5, you get 1.5 over 5 times sine of 85 degrees equals sine of b. Then we can dump this left-hand side into a calculator. So 1.5 divided by 5 is 0.3 times sine of 85 degrees. I get 0.29885 and change, so 886. And that's sine of b. Okay, well, that's sine of b, but we wanted to find b. So we should use an inverse trig function. So we'll apply inverse sine to both sides. Right, so inverse sine of that messy number, I get 17.39 degrees. Right, so there's the angle B. But actually, there's something we have to be a little bit careful about, because if you draw the most important diagram with the unit circle, if you're in a unit circle, sine is a y-coordinate, so a y-coordinate of this value would 0.29 something. That's like this. And it looks like there are actually two possible angles. There's this small one, which must be 17.39 degrees, and then there's this big one, which, well, the big angle is just a half turn, but then with this tiny wedge here taken away. But that tiny wedge is the same size as the small angle on the right. So it's 17.39 degrees. So this big angle here is 180 minus 17.39. So that's 162.61, I think, if I did my arithmetic there. So we found that there's actually two angles B that might be correct. It might be this smaller angle, and it might be this bigger angle. But wait a second. If this is B, right, way up here, A was 85 degrees, and an angle that's 162 degrees and an angle that is 85 degrees won't fit into a right triangle. This is just too many, I'm sorry, won't fit into any triangle. So this is just too many degrees for a triangle. So this B actually can't work. So it looked initially like maybe there were two angles that might work for B, but in fact there's just one, 17.39 degrees. So you can see if you know an angle and an opposite side, then you can use the law of sines to get some information about other pieces in the triangle.